Welcome back to our series on electricity and magnetism. In today's episode, we're going to explore the origins of the magnetic field. That is, we're going to open the door to electromagnetism and look at a unique formula called the law of Biot-Savart. Well, what are the origins of the magnetic field? We've already looked at some implications of magnetism. Well, it turns out that magnetism is entirely an electrical phenomenon. If I take a positive charge that's flying through space, of course, that positive charge has an amount of charge and it's moving at a velocity. Well, what it does around it is it creates a packet of magnetic field. The magnetic field circles around the path of the charge and actually follows the right-hand rule. So if I point my thumb in the direction of the velocity, then my fingers are going to curl in a circle around that trajectory, which is an indication of the magnetic field. So it will be moving up towards you and down towards me. And in essence, those little orbiting magnetic fields get larger and larger the closer to the particle we get. Right on top of the particle, they're actually quite large. And then they shrink again to become smaller and smaller, ultimately disappearing in the path behind the particle. So it's almost like a little packet of magnetic field that follows the charged particle around. Well, what's the size of this magnetic field? We can see that it curls around it in a circular path. Well, it turns out the size of the magnetic field is based on a cross product. Its magnitude at any point along that circular path is going to be equal to really three parameters. The first is the size of the charge. Bigger charges form larger magnetic fields. The second is the velocity vector. The faster the particle moves, the bigger the field that it generates. And that will be crossed together with the radial vector. That is, at any point on the magnetic field, if I point a vector back towards the particle, that will be the radial vector. And then I divide this whole thing by the radius itself squared. That is, magnetism, similar to the electrostatic force, is an inverse square field. Now, of course, I've set these equal. In reality, there's got to be a constant of proportionality in front of it. So in reality, this is more of a proportion. That is, the size of the magnetic field generated by a moving particle is proportional to the cross product of the velocity and the radial vector, and it's inversely proportional to the radius. Let's formalize this by actually inserting not just the constant of proportionality, but changing a moving charge into the current in a wire. In essence, we want to change the quantity QV into the quantity IDS. And that will then develop for us what's called the law of Biot and Savar. So let's take a look at a current flowing through a wire. So we've got a copper wire in space, and the shape of it doesn't really matter for now. What I want to do is identify, hey, this current is like a stream of particles, which means I know at every point in space around it, it's going to form a magnetic field. And I even know that that magnetic field, following the direction of the wire's current, is going to curl around, coming towards me in the top of the wire and under me away from the wire. So it's going to form, in essence, magnetic field lines that look like this and curl around it. Now, these magnetic field lines will get larger as we're closer to the wire, and they'll get smaller as we move away. Okay, well, let's imagine a point in space, and what I want to do is I want to actually calculate what is the magnetic field intensity right here at this point. Okay, I'm going to need a couple of things. First, I'm going to have to identify a short segment of this current, because what I need to do is define just how much charge is flowing along that short segment. So I'm going to define that as ds. And its direction is going to be defined in terms of a little vector that's tangent to that point and runs in the direction of the current. The next thing I need is a second vector that actually points from this area right back towards the location where I want to measure the field. And along that, I'm going to draw a unit vector called r hat. This will be the radial vector, and it will point in the direction to where I'm going to actually evaluate the size of the magnetic field. Final thing I need is the actual distance in between the location where the current is and the location where I want to find the field. That's going to be the radius itself, and it'll be a scalar value. The r hat vector provides direction, but r really provides the magnitude of how far away it is. Okay, it turns out we have everything necessary in order to derive what the magnetic field is at this location. And then we'll be able to use the right-hand rule to kind of determine the direction of the field at this point. Okay, so this dB will calculate the amount of magnetic field at this location due to this little tiny piece of segment that's generating it. First of all, the constant of proportionality that would have come from this had we actually been able to evaluate this completely. It's mu naught times I, the current, over 4 pi. Now, mu naught is very similar to epsilon naught. Epsilon naught was kind of the way in which space responded to the presence of an electric field. It was called the permittivity of free space, and it was the ability for space to sort of allow that that electric field to flow through it. Well, this is a similar quantity. This is called the permeability of free space, and the permeability of free space is a constant that represents exactly how free space responds to the presence of a magnetic field. It's very strongly related to E naught, although E naught was related to Coulomb's constant. Of course, we have no Coulomb's law for magnetism, so mu naught is the only game in town for calculating magnetic fields. Well, so far, this is just the coefficient of the actual relationship, and the actual relationship matches the one we've defined over here. It's going to be ds, whatever is the direction of this vector along the current. So it's going to be defined by the path that we choose to do the integral, crossed with the r hat vector. And of course, the r hat vector is defined in terms of the location where we're evaluating the current, directly back towards the location we're evaluating the magnetic field. And it's always a unit vector, so it'll only have a magnitude of 1. And then that whole thing will be divided by r squared. And there it is. This is called the law of Biot and Savart. Biot-Savart is sort of how we calculate the amount of magnetic field at any location due to a flowing current. The theory is a moving charge generates a magnetic field, but of course it's hard for us to control a moving charge through space. Much easier to control the current in a wire. So this is the magnetic field generated by a current in a wire. And this opens the door to a whole new phenomena for us, and that is, it's the fact that magnetism is not a separate phenomena in and of itself. Magnetism is an aspect of electricity because magnetism has no magnetic monopoles, particles that generate the force and the field. Instead, magnetism is simply a manifestation of moving charge. When charge moves, it always generates a magnetic field, and this is the relationship we use to find it. Okay, let's apply this for an example. And the example I'm going to pick is just about the easiest current carrying wire I can imagine. And that's a long straight wire. So we're going to draw a current carrying wire. It's going to carry the current in that direction. I'm going to drop a line straight down to a point in space. This is where we're going to evaluate the size of the magnetic field from the wire. It'll be a distance a away, and this will be the location where I want the field. So once again, I've got to select a little section of this in order to determine where my ds is going to be. So ds is going to be the distance that we travel along that direction. I'm actually going to integrate this by laying the x-axis right on top of it, so ds is really going to turn into dx. But for now, let's just leave it as ds. And then I draw a line from my little current packet straight back towards the location where I want to evaluate the field, and that's where I draw my r hat vector. R hat then points directly from that location back to where I'm evaluating the field. Okay, I'm also going to need the total distance along this line. I'll call that the radius. And of course, because I'm going to evaluate this along the I wire's current, I'm just going to throw an x-axis right on top of this, so the x-axis will extend outward and go back this way. I'll put 0 on the x-axis right here. So this dimension right here is just going to be the x we happen to be at the time. That's going to allow me to evaluate a couple of things because in essence I've got to substitute into here. This will feel very familiar because it's almost identical to the process where we evaluated electric fields at any point around a charge distribution. You remember at the time that first we had to define what dq was. In this case, we have to define what ds is. And the second thing is we determine what the radius was. ds will determine exactly the integral limits that we're going to use and sort of the geometry we're going to exploit. We'll also have to evaluate this cross product in the top, but let's first sort of substitute in what we found so far. So first, the radius, r squared, is going to be equal to a squared plus x squared. So that takes care of the quantity in the denominator. The nice thing is r hat has a magnitude of 1, so I do have to worry about its direction, but I don't at all have to worry about what its magnitude is. The next thing I need is to evaluate ds. Because I'm going to integrate along the x direction, ds just becomes dx. And so I think I can build this integral now. dB should be equal to, first, all the constants, mu naught and I and 4 pi. And now we get to the integral itself. Well, let's give this guy some limits of integration. I'm going to say that the wire we're interested in has a total length of L. And if we've started in its center, then this is negative L over 2. And over here at its end would be L over 2. So those are my limits of integration. I'm going to integrate from negative L over 2 to L over 2. And what am I going to integrate? Well, I'm going to integrate ds crossed with r hat. So that's dx crossed with r hat. And then the whole thing divided by r squared. And of course, r squared is a squared plus x squared. Well, I'm not quite done yet. What I need to do now is evaluate that cross product. Fortunately, these both lie within a plane, so I know what their direction is going to be. If I go ahead and use the rules for a cross product, I need to point my thumb in the direction of ds and my remaining fingers in the direction of r, and you'll see what that does. My palm points right there in your direction, and that means this field is going to curl over the top and under the bottom. At this point right here, the field will be going directly into the board according to this cross product. So right here, I put a circle with an X in it. That's the direction of the magnetic field right there at that point. And even if I move this all the way along the line, that will always remain the cross product. The cross product direction will point into the board at that location for every location that I'm integrating. So I don't need to take into account the fact that the direction of the cross product changes. It remains constant. But I do have to take into account what the magnitude of the cross product is. What is r hat crossed with dx going to look like? Well, it's really going to be r hat crossed with dx, and it's going to be r hat dx times the sine of theta. The magnitude of a cross product always includes the sine of the angle between them. And of course, that angle would be right here. Fortunately, for the sine of an angle, whether the reference angle is greater than or less than 180 makes no difference, or excuse me, greater than or less than 90, which means this angle here can be used just as easily as the reference angle. And you can see that the sine of that angle will be its opposite side over its hypotenuse. That's a over r. So the sine theta actually becomes a over the square root of a squared plus x squared. Well, we can substitute that in, removing the cross product. The magnitude of r hat is 1, so it doesn't need to be there. So now I have my complete integral. It's going to be mu naught I over 4 pi, which is a constant. The integral from negative L over 2 to L over 2. And now we can replace all of this. There'll be an extra a squared plus x squared under the square root in the denominator, plus a full one, so that's a squared plus x squared in the denominator to the 3 halves. And then the numerator quantity is just going to be a dx. Well, a is a constant too, so I can go ahead and pull that out. But let's go ahead and perform the integral. The integral of dx over a squared plus x squared is actually equal to, again, rewriting the constant, mu naught I over 4 pi, and then we'll put the a here. And then here's what the integral evaluates to be. It's going to be 1 over a squared, and then what's left over is a squared plus x squared to the minus 1/2. And that'll be evaluated between negative L over 2 and L over 2. Once we do the substitution and we sort of clean everything up, here's what we end up with. It's mu naught I over 4 pi A. And then here's what's going to be left once I make all of that substitution. We're going to end up with L over L squared over 4 plus A squared over 4 to the 1/2. And that is the magnetic field at this location going into the board for a current that runs in this direction between L over 2 and negative L over 2. That is if the wire's length is L. But what's far more interesting to us is what happens as the wire gets longer and longer and longer. That is, we really want to know the magnetic field of an infinite wire, or at least semi-infinite, so long that we don't have to worry about the ends because they're so far away. Well, as you can see, it doesn't affect this part of the integral, it just affects this part. So as L gets larger and larger and larger, then L squared over 4 simply becomes infinitely large. So large that this denominator becomes L squared to the 1/2 under L. So this simply turns into 1. I can pull a 4 out as a 2, so a coefficient of 2 basically exits. And as L goes to infinity, this entire quantity goes to 2. And that produces the final answer, which is mu naught I over 2 pi A. And this right here, that is the magnetic field from a very, very long wire. And it doesn't matter where you move on it, up or down, the magnetic field will fundamentally be the same at every location based on the current. It is a function of how far away we are, because remember, A was the distance we were from the wire. It's kind of like the radius. As I move closer to the wire, the field gets significantly larger. And as I move further away, it gets smaller and smaller and smaller. It's an inverse field. It's not an inverse square field, but that's the magnetic field of an infinite wire. And we were able to calculate it directly as a result of the law of Biot-Savart. Biot-Savart can be applied easily anytime you can set up an integral to find the magnetic field at a location, and then you can exploit the geometry easily in order to actually perform the integral. There will be a number of situations where symmetry allows us to directly calculate the magnetic field. But fortunately, just like we did back when we calculated electric fields manually, we're going to find out there's an easier way that utilizes symmetry and a fantastically powerful shortcut, which we called Gauss's law for electrostatics. And Ampere's law is going to come to our rescue here. And that's our next lesson.